Hello everyone, and today in this video I will talk about normalization and how we can do normalization of the vectors. And this is the really interesting concept, how we can normalize the age factor of the particles or any like attribute if we have age. And I have talked about this age concept and how normalized age is its whole life. I will do the same, but I will cover these two concepts together so we can have the similarities and we can make the connection here with this single concept. And I have created some notes, and it will be more easy for you and for me to explain if I have these notes, but I will start with the empty blackboard, and then I will jump to Houdini and we will do these concepts, and we will see each concept with an example. First, I will just say normalization, or you can use normalization like S. So both are correct, but I'm just using Z. Okay, I will just say, not draw. I will say, let's start with a vector like we always do. This is my vector, which is P, and it has X, Y, and Z, and W, which in this case, I will not think about it right now, because when we calculate the length or magnitude, it says 1 square, so it will be 1, so that's it. Okay, or it will be 0 when we only talking about the direction. I talked about this in the 4x4 matrix yesterday. So let's talk about these two. So I have this vector, and a vector contains two things. First, a direction. Second, its length, or we call it its magnitude. So I will just write it here. We have a magnitude TUDE, and I'm writing with my mouse, so you can ignore the writing. And we have its magnitude and direction. Magnitude, we call this length also. Okay, so we have two things, length or magnitude, and its direction. So normalized vector is a unit vector with one unit as its magnitude or length. So the length and magnitude will be one unit, and we call it a unit vector. So when we multiply 1 with other things, other mathematical data, so we will get the similar data, right? That's why we use the magnitude as 1, because if we use 0, then it will be like the final result will be 0. But if we use 1, the final result will be the same. That's why we use 1, and we call this a unit vector, so we can only have the direction part. And how Houdini normalize a vector, how we can normalize a vector. So for normalization, to make anything like of one unit, the magnitude of one unit, first we need to like know what's its magnitude and what's its length, right? Because that's what we need to have its magnitude and the or length. So to calculate this, we use this Pythagoras theorem, but we are using three components. So it's something like x square plus y square and z square under root, and we will get its length or its magnitude, right? And this final length and magnitude will be like x by its final length or magnitude, right? Similar y its similar final length or magnitude, and it goes with z. And if you have w, and it will work as w if we are using the fourth component vector. But this fourth component vector is for translation, right? To calculate the magnitude, we use like three components, so we don't need to worry about this, or we don't need to worry about this, because we will not calculate this by our hand. We will just use the concepts, and Houdini will calculate it for ourselves. So we know this. So we know that we just need these, we need the final value, and we just need the its magnitude or length. And if we divide each component with its final its magnitude or length, we will get the vector normalized. So how we do this in Houdini? Let's start fresh, right? Let's create a sphere. Wait a second. It's okay. We have this sphere, and I will call this nothing, and I will just put it a normal. So I will just visualize this, and I will points. I have this normal, right? So now each point has a normal which has a direction, but this normal, let's see what its magnitude. So I will say point wrangle, and I will use the length function. So I will say v attribute v, or I can say attribute normal, let's say float attribute norm equals to length, and we will use its attribute n, and it will be a vector. So we'll use this, and you will see the norm value we will get, it is 1. So now we know that this normal we created has a magnitude 1 by this, because this length function will give you its length. We can do the same by attribute warp or point warp, and you go inside and you have this length function here. So you will just have to see the normal length. We just need to give the normal its length, and we just have to say you can create a new bind export, and you will see we can say this it's a float, and we can call this new norm or norm warp. So we will know that, and you see that its length is 1 here. So we know that when we put a normal on something, its value, its magnitude is 1. But what if we want to normalize a vector? So what we can do now? And I will do the same here. I will just create a point or add a point, and I will just look at this, and you see this point doesn't have a normal. So we will create an attribute which we can visualize, and for this I will just use the velocity attribute. So I will just randomize the velocity, and I will say the value like 20, and when you visualize this, you can just visualize it here, you will see something like this. So now we have a point with this velocity attribute, and we can see its direction. We can see this vector v is pointing in this direction and has a magnitude. How we will calculate the magnitude? You can just calculate it by point warp, and inside this, not warp, point wrangle, and you connect this, and you will see. So we can create a new attribute. You can just say f float attribute norm, this is for normal, and we will say v equals to, so how we can like calculate its length? We can just say its length attribute, and we can say vector attribute vector, vector attribute velocity, and you will see we have this its length. So you will see its length is not 20, because what is happening here, first the randomized value is from 0 to 1, right? So each component will get a value between, I will just use this board and I will explain it. So we have the randomized value. So we are randomizing this attribute v, which is a vector, and we are giving this three component x, y, and z, and the minimum value we are giving this and the maximum value we are giving this is from 0 to 1, right? And we have another thing which is global scale. So when I open Houdini, you will see this global scale. So what is happening here? I will say 20, and you will see our this vector length increased when we increase the global scale. And what is happening here? So let's say x, y, and z, we are getting a value from this. So this value, let's say if we have 0.3, if we have 0.7, and if we have 1 in z, so this global scale value, if it's 30, then the final value will be 0.3 multiplied by 30, and it will be 0.7 multiplied by 30, and it will be 1 multiplied by 30. So you will get the final value based on this global scale, but the base value will be controlled from this minimum and maximum. So the minimum value is 0 and the maximum value is 1. If you say I want the dimension to be 4, then you will have 4 components, but in this case we only have 3 components, and you can say that the normalized v, the normalized vector v is now 15. Not normalized v is just length. So now we know that we can calculate this its length from this. So I will create a float which is a variable, and it will be here only. A float name, let's say length equals to length, and we will just we will just say the length will be v attribute v, and just this. So it will be this. So now we have its magnitude, its length. Now what we will do, we will normalize this vector. And how we normalize this vector? We will just say v attribute v, because we are normalizing this vector, so we will put this same vector. We are normalizing the v vector, so we will put the final value of this v will be v attribute v divided by its length, which is a float variable here. So you will see now it has normalized, and this value will be this. And when you calculate the magnitude of this vector, which is x, y, and z, when you calculate the magnitude of this vector, it will be 1. So that means we have a normalized vector v. And a crucial thing here is, when you normalize a vector here, a vector consists of x, y, and z, or 4 components or 3 components, you get each individual value from -1 to 1. Not more than this, because anything in between this will give you the magnitude or length 1, and you will get -1 to 1, but your length will always be 1 unit. So that means your vector is normalized now. And to, if we have this normalized vector, how we can put it back to where it was, like how we can give the magnitude it had before normalization. And to do this, we just have to say equals to v, we can say v attribute, oops, v attribute v and multiply by its length, and you will get the same value you had here. In this case, you will get this length, and if you calculate its magnitude, you will get the same magnitude as this. If you want to do this also, and you can say attribute, or we can create a new attribute, right? So we will say float attribute norm, or float attribute magnitude, magnitude, and you will get v attribute v, we can say length, and we can say v attribute v. It will give you its value, which is 15.5098. And now we know this, and this function we can write it in a different way, which is this v attribute v, and you can say multiply equals to length, and you will get the same thing, because this function is similar, and we call this. I have created this video, yeah, this not, sorry. So we can write the code by two ways. We can put like the vector and multiply by length, or you can say vector star multiplication equals to length. That means whatever is behind this, whatever vector behind this will be multiplied with the thing that is equals, which is after the equal sign. That means if you put plus or minus, that means this vector will be multiplied, or uh, you know multiplied, or addition or subtraction we can do here by this way also. This just says we don't need to write the same, like write this by 2 times, so we can just say multiply this by this length, and you will get the value you need. So it's a shorter way, but it's like the similar way. And when we normalize this, we have another way to normalize this, which is we can just say v attribute v equals to normalize v attribute v, and you can get the same value here also. So if I create where is this thing, if I create another point wrangle, and if I'm saying float, this is the float variable, magnitude, I will use magnitude this time, and we have length, and let's say v attribute v, we will calculating this length, and if I'm saying v attribute v equals to normalized normalize v attribute v, you will get the same thing here. See, it's been normalized. You don't need to put this here. This is just the like magnitude and length of this, and you don't need to do that here, the division also. And one more thing, in this you don't need to divide each component by the magnitude or length. You can just say v attribute v or any other attribute that you have, and you just divide it by its length or magnitude, and it will do like this division, this individual division behind the scene by itself. So you don't need to worry about that also. So now we understand how we can normalize these things, right? And how we can put back that same thing. And you can do this in attribute warp. So I will just use point warp because it will work on points, because we are only working here with points. So you have this length, right? And you have this divide. And what you can do, just you need to get the v and you need to divide its total length. And how you can calculate its length? By doing this, and this will be your null, and you can say this is our normalized vector. And when you put this into, like, you can put it any other, let's say bind export, and you can say result, something like that. So you will see that this is not normalized right now, this is not normalized, this is normalized, and you will get the result this. And you can just calculate its magnitude also by putting this is the normalized vector, and you can say length, and you will get 1 as the result, because you are now calculating its magnitude. Okay, so now you understand. And if you want to do the same like the normalized vector, you can just multiply it with its length, and you can see the result you have and you can just put it right here, and you will see you will get the result 15, which we had before we did all this. And you will get 15, which we had before we did all this normalization. So we understood that the final length, the magnitude and length, will be root x square plus y square plus z square. The final value will be the random value from 0.1 global scale for each when we are randomizing this. You understand this? The minimum value and the final value, the maximum value will be from 0 to 1, and the value for each component will be multiplied with the global scale to get the final value. Also, you have this normalization. You can just say x divided by length, its magnitude or length. You just need to divide each component by its length, its final magnitude, and you can just simply put the vector and divide by its magnitude, and you will get it normalized. And I also told about the value that the value after normalization of each component will be from -1 to +1, and the magnitude value and the final value of that whole vector will be 1 unit. And this is about the code. You can write these code by yourself. One more thing I talked about when we were like when I was working with particles, I talked about that n age equals to life, and n age here is normalized age of these particles. We can create a simple setup here so you can understand this better, because this is like a crucial setup also. Let's create a sphere. We have a sphere, scatter points. You can say relax iterations, because I want them as dense as possible. You can say attribute wrangle, and you can create age attribute from here, or you can just say popnet and you can create this was a bug. I can say amplitude 4 and roughness let's say 0.3, and you will see we have something like this. What I need to do, I just need to turn off the visualization for the velocity. So we have something like this, but we don't have the life attribute on these particles, so they will just they will never die, right? They will never die if we don't have the life attribute. So we need to give them a life attribute. What I can do, I can give each particle a similar life, or I can give each particle a different life, but in a like similar range or something. So I will just say point wrangle, and I will give this a life. So I will say float attribute life equals to I will say fit, or you can say random, rand, and you can say attribute pt num. So you will get this life, but it will be like random numbers based on these pt numbers, and this random number will be from 0 to 1. And if you want to increase this, what we can do, we can fit this, and we can fit this into another range. And what I mean by that, you can say fit 1, fit 01 means the value that we are getting from the value we are getting is from 0 to 1, and this random pt number is giving us 0 to 1 value. And what we can do, we can just say random, you can say random, and you need to give it like, now what do you want? I want 0.3 to 1.5, something like that. And you can say now we have something like that, and I have created a simple note. Here is this code which I'm using, fit 01 value, which is the value that we are this is the input value that we are getting. And input value here means the, here in this case, the input value is this random pt number, because we are just giving some random number to each point based on this pt number, and that is going into the this life attribute. So you will, if I open this, and you will get this minimum new value and the maximum new value, and you will get here. Okay, so I have something like this. So now these particles have their, like these particles now have their life. If I increase, let's say the minimum is, let's say 0.5, and the maximum is 2, so we will see something like this. So now they are like have more life. And now what I can do, I can randomize, like I can normalize their age, normalize age, and it will be equals to their life. Because here one more crucial concept here is, we have age. Age means how long they like are in the scene, like from their birth to this time frame now, which is here. Like if these particles are born at 0, now at 24 frame they have a life of 1 second. They are born for like 1 second, and we have their life. Life is their complete lifetime, and we can represent this from 0 to 1. We can like use this life, and this is their entire period. So if I'm saying that if a particle has life of 4 seconds, that means at 1 will be 4 seconds and it will die. That particle will die. And we have this age. So if we normalize this age, and what is the maximum value we can have here is their life. If we say, so we will get an age, and this an age will be in between 0 to 1, and it will be equals to its life. Because life, we can put it in 0 to 1. 0 means birth, 1 means death, and here n age is also in between these two. So that means n age equals to life. Normalized age is equals to their total life. How we can do this and how we can understand it here? You see, if I go inside here, we have pop print. I can say pop color, and I can use this Vex expression here, and I can say ramp. You will see this ramp is saying that this ramp is an age, and normalized age of these particles will be their life. Because when you normalize the age, just remember this, when you normalize the age, you will get the value from 0 to 1, and you can put this 0 to 1 as in a ramp that also represent its life, because you can put the its own whole life in 0 to 1 number, so it will be easy for us to put it in ramp and use this in different methods. So we have ramp and normalized attribute and age, which is normalized age, and we have this here without normalizing it ourselves if we create this pop net. So you see, this black color means they are not born, like they are at 0. And when they will born, they will start from this color, and when they will die, they will die at this yellow. Yellow means their life is done and they are dying now. You see? So we know that each particle has its life. We had put it life here, ramp, which is their life, and age, and we have this color. I will just delete this. But one more thing here, I explained that day. You see this range? I will explain it here. We have this 1, 0, 1. This is an age or life of a single particle, right? This means death, this means birth. If I'm saying it will die at 4 seconds, this 4 second is a constant. After 4 seconds, the particle will die. This is the truth. You cannot change the truth, and it's hard coded that after 4 seconds, this particle will die. If I stretch this range to 0 to from 0 to 1 to 0 to from then 0 to 4, that means this is hard coded. That means the timeline will move, but when it will move, these particles will die at 4 seconds, and this 4 second will be here now. But the real difference that these concepts make is when you are fitting something into another range. For example, 1 to 4 and 0 to 1. Sorry, 0 to 4 and 0 to 1. It's 50%. That means it's half. If a particle is standing here, half of this range, and its value is 0.5. So what will be the value of this particle in this range? It's half, 50%. That means its value will be 2. But it doesn't apply when you have a hard coded number, and that says after 4 seconds these particles will die, no matter how you stretch, how long you are long you are making this ramp, they will die after 4 seconds. So even if I say the ramp is now 4 here means they will die after some seconds. That means you will see when they are dying like here. They are dying like here. It was from 0 to 1 here. Now we have extended it 4 times. That means at 25% these particles will die. If you say 2 times, that means they will die half of this range. I hope you understand this. I have explained this concept when I talked about these particles for the first time. But just remember this. So we can just delete this. And after this pop net, we can say point triangle. And here we can say that we can normalize their age here, and it will be equals to their life. How we can do it? So we can say attribute norm age will be, and I will say it's a float, and we'll say normalize age will be its. How we can normalize this? First, let's calculate we know its life, right? Yes, we have this their life attribute. Where is it? We have its here. We have its life attribute for each particle. So what we can do, and this code will run for each particle. So we are just typing an expression, f attribute normalize age, you can say this will be equals to age attribute age float attribute age divided by float attribute life, and you will get their normalized age. Here you will get the value between 0 to 1, and this will happen after this, and you can put this normalized age, and like you can use a color node, and you can say random ramp from attribute, and you can say normalized age. You can use inferno, right? And when you see this, you will see now we are having the same result as we had, right? So we are just, we have their age normalized, which is now their life, and life goes from 0 to 1, and we can put this 0 to 1 value into this ramp, and we can manipulate these points, manipulate this CD color attribute by this ramp, and you will see something like this, right? Okay, we can do this by warp also. So when I say point warp, and now we have their age and life, so you just have to divide, and you have to divide their age by life, and what you will get, you will get a, I can just use null, and you will get a new attribute which is an age, which is their normalized age, which you can put it in a ramp, and or you can just say not this one, ramp parameter, and you can put it here, and we are using ramp, and this is inferno, right? And I am putting like this here, and I can just say this, and you can go inside here, and what I can do, right, I can put this value into this normalized age which I created as bind export, or I can put this ramp value into the CD, so you will get the similar results. Because if you not connect this into the CD, then the data doesn't flow, like there is no, you are not outputting it. You can output it into bind, or you can just create a bind export node, and you can create your CD attribute, and you will get the same result as we were getting with this. So we understood today that the normalization doesn't only limit it to the vectors. We can normalize this single thing, this other thing here, which is age, and how normalized age is equals to the lifetime of those particles. I hope you understand that here now. So we also learn this, how we can normalize any attribute. We also learn these things to calculate the magnitude and length, and we learn these, that these two codes are similar, and how we can store that float value here. So this is it for this video, and I hope you understand how do we normalize things. I could use this video as myself to, I consolidated the things that I learned. Also, it can be like a learning document for you also, or I can just, I can just made this video a bit smaller, like a bit smaller, but yeah, I didn't, because I needed to have this concept ready in my brain also. So yes, this is it for this video, and I hope you understand something, but I really understood a lot of things here. So yeah, I will see you in the next one. Until then, take care.